the gas laws. The gas laws are the Boyle's law, Charles' law, and the pressure law. Boyle's law says that the volume of a fixed mass of a gas is inversely proportional to its pressure, provided temperature is constant. Volume is inversely proportional to pressure, temperature constant. In equation form for Boyle's law, V1 P1 is equal to V2 P2, equation 1 here. By this we mean the volume at the pressure P1 will be equal to the new volume at a given pressure. That's the product of the volume and the pressure at a given time will always be equal to the product of the volume and the pressure at another given time, provided temperature is constant. Graphical illustration of Boyle's law is shown here. It's a curve if it's graph of volume against pressure. But it's a straight line graph starting from the origin. If it's a graph of volume against the reciprocal of pressure, or graph of pressure against the reciprocal of volume. Charles' law states that the volume of a fixed mass of a gas is directly proportional to its absolute temperature, provided pressure is kept constant. Volume is directly proportional to absolute temperature, that's the Kelvin temperature. In equation form, V1 divided by T1, V1 is the initial volume, T1 is the temperature at that volume, will be equal to the new volume as the new divided by the new temperature, equation 2. Charles' law is represented graphically as shown below. If its volume against temperature in degrees Celsius, the graph will look like this. But if it's volume against temperature in Kelvin, then it will start from the origin. Pressure law states that the pressure of a given mass of a gas is directly proportional to its absolute temperature, provided the volume is kept constant. Pressure is directly proportional to temperature in Kelvin. P1, T1 is equal to P2 divided by T2. We take this as our equation 3. And below is the graphical illustration of pressure law. Graph of pressure against absolute temperature. It starts from the origin and it's a straight line graph. An ideal gas is a gas that obeys all the gas laws. For an ideal gas, pressure times volume divided by temperature is always constant. In other words, P1 times V1 divided by T1 is equal to pressure 2 times volume 2 divided by temperature 2. The temperature being in Kelvin. Example 1. A selected flask contains 600 centimeter cube of air at 27 degrees Celsius and is heated to 35 degrees Celsius at constant pressure. The new volume is A. 508 centimeter cube, B. 516 centimeter cube, C. 608 centimeter cube, and D. 616 centimeter cube. Solution. From the question, we are given the initial volume V1 as 600 centimeter cube, initial temperature T1 as 27 degrees Celsius, which we must convert to Kelvin, 27 plus 273 in Kelvin. So T1 will give us 300 Kelvin. We are also given the new temperature T2 as 35 degrees Celsius. We have to convert it to Kelvin. That will give us 35 plus 273 in Kelvin. Temperature 2 will give us 308 Kelvin. Then we have to find V2, the new volume. Pressure is constant. This question is a relationship between volume of a gas and temperature, and we are told pressure is constant. From what we studied so far, it has to do with Charles' law. So we have to apply Charles' law equation. From Charles' law, V1 over T1 should give us V2 over T2. So V1 is 600, T1 is 300, V2 is what we are looking for, and T2 is 308. 300 we cancel here to give you 2. This means that V2 is equal to 2 times 308. V2 is 616 cm3. By this calculation, option D is correct. Example 2. When a fixed mass of an ideal gas expands at constant temperature, which property of the gas molecules increases? A. Average separation. B. Average number of collisions per unit time. C. Average speed. And D. Average kinetic energy. We'll review the options based on what we know about properties of gas molecules. Now, when the gas expands, the volume will increase. So for option A, average separation, if the volume increases, the molecules will be separated in a wider form from each other. So option A is correct. So I have option A correct. Let's consider option B. The average number of collisions per unit time. Average number of collisions per unit time increases. That is not correct. When the molecules are widely separated due to expansion, the number of collisions made per unit time reduces. So, A is correct, B is wrong. The average speed. The average speed of gas molecules is a function of its temperature, the temperature of the gas as a whole. So since the temperature is constant, it is expected that the speed of the gas molecules should be constant and it should not increase. C is wrong. Average kinetic energy is a function of the average speed. So if the average speed is constant, the average kinetic energy of the gas molecules should as well be constant. Therefore, there should not be any increase. D, increase in KE is wrong. So by this explanation, option A is correct. Example 3. The tire pressure of a car was found to be 150 centimeter mercury in the morning at a temperature of 27 degrees Celsius. Hard driving in the afternoon raised the temperature of the tires to 57 degrees Celsius. The tire pressure had by that afternoon dash. A. Decrease by 15 centimeter mercury. B. Increase by 15.0 centimeter mercury. C. Decrease by 22.50 centimeter mercury. D. Remain constant. We make use of the information provided in the question itself. We are given the initial pressure P1 as 150 centimeter mercury. We are also given the initial temperature T1 as 27 degrees Celsius, which must be converted to Kelvin. 27 plus 273. T1 is equal to 300 Kelvin. Now, due to hard driving, the temperature increased to 57. T2 is 57 degrees Celsius. Converting it to Kelvin, we have 57 plus 273 Kelvin. And that will give us 330 Kelvin. We are asked to find whether there will be a change in pressure, increase, decrease, or pressure remaining constant. To answer that question, then we must get the pressure at that higher temperature. The value of that pressure will now help us to assess the position of the tire in terms of pressure. Now, from the information gathered so far, the relationship is between pressure and temperature. And of course, the volume of that air, which is the gas, in that tire is constant. It does not change. So the law that applies here is pressure law. So we use pressure law equation. From pressure law, P1 over T1 is equal to P2 over T2. P1 is 150, T1 is 300, is equal to P2 over 330. 150 here, 150 here, 2. So we have P2 is equal to 330 divided by 2, which is 165 centimeter mercury. The initial pressure P1 was 150 centimeter mercury, and the pressure after driving P2 is 165 centimeter mercury. From this result, we find out that the pressure has increased by 15 centimeter mercury. Pressure has increased by 15 centimeter mercury. So, option B is correct. Example 4. A fixed quantity of a gas is subjected to various pressures P and the corresponding volumes V measured at constant temperature. Which of the following graphs best explain the result? We have graph 1, graph of pressure against volume, graph 2, graph of pressure against the reciprocal of the volume, 3, graph of pressure against volume, and 4, graph of pressure against volume, a different pattern. The options are A, 1 and 2, B, 2 and 3, C, 3 and 4, D, 3 and 4. To answer the question in example 4, we must recall what we know about pressure-volume relationship of a gas at constant temperature. This is all about Boyle's law, and that law tells us that for that fixed quantity of gas, the pressure is inversely proportional to the volume. Pressure is inversely proportional to volume, or volume is inversely proportional to pressure, provided temperature is constant. If we look at the first graph, it's a graph of direct relationship between pressure and volume. So number one is wrong. The relationship between pressure and volume at constant temperature is an inverse one, not direct one. Number one is wrong. The second graph is a graph of pressure against the reciprocal of the volume, and that is exactly graph of Boyle's law, which is stated in the question. Number two is correct. Graph number 3. Graph of pressure against volume. From the look of that graph, we found out that it shows that at the time there won't be any gas at all, because the straight line cuts both axes, both the pressure and the volume axis, and a gas can never cease to exist. So graph number 3 is wrong. Number 3 is wrong. Graph number 4 shows an inverse relationship between pressure and volume, which is correct for Boyle's law. Number 4 is correct. So from this assessment, we find out that the option that is correct is option C. Option C is correct. 2 and 4.